So we see that the rate of reactions decreases as the reaction goes on. Now, the result of that is the lowering of the concentration. As the particles become less concentrated, you get less of them reacting. Now, we can actually use that relationship between the concentration and the rate to find out some interesting things about the reaction. So we're going to focus next on the concentration and how that affects the rate. And again, in particular, we're going to be looking at that instantaneous rate at the beginning of the reaction. So here we have a reaction between the ammonium ion and the nitrite ion. Some of you might remember this as actually the net ionic equation. Remember this from our semester 1 exam in honors chemistry. And the data that we have here, there are 8 different times that this reaction was run. Each time the initial concentration of the ammonium and the nitrite ion were changed. And what was observed then was the initial rate of the reaction. So you can see how that varies here. Now what we want to do is see if we can glean some information out of this as to what happens to the rate when we change the concentration. If we compare experiments 1 and 2, in these we double the concentration of the ammonium and trying to keep our our conditions controlled. We kept the concentration of the nitrite constant. So again, you can see the doubling of the concentration here and the initial concentration of the nitrite constant. And what we see from that is by doing that, we get a doubling of the rate of the reaction. Right? So what this shows us is that doubling the concentration of the ammonium ion doubles the rate of the reaction, or the rate of the reaction is directly proportional to the concentration of the ammonium ion. Now, if we do a similar comparison between experiments 5 and 6, where we have the concentration of the nitrite doubling, and we've kept the concentration of the ammonium ion constant, we can see again that there's a doubling of the initial rate of the reactions. So therefore, doubling the concentration of the nitrite doubles the rate of the reaction. So again, we have a relationship between the rate of the reaction and the initial nitrite concentration. So they're directly proportional. If we take the two of these things together, and we say that we have the rate of the ammonium ion is proportional, or the rate is proportional to the concentration of the ammonium ion, also proportional to the concentration of the nitrite ion, and so we can come up with a proportionality expression for both of those. And of course, we know that if we have proportionality, all we need to do is add a constant right here to determine or to change that into an equation. And this equation is what we call the rate law, and K is the rate constant. Now, once we have the rate law, one of the things we're going to need to do is to be able to determine the value of the rate constant. It's actually fairly simple. Once we have that rate law, we can rearrange it to solve for the constant. Constant would be equal to the rate of the reaction divided by the concentration of the ammonium ion times the concentration of the nitrite ion. Right, so these would be the initial concentrations. So where do we get these values from? Well, we have a whole set of data back over here. So I'm just going to use the data from experiment number 1. So obviously we could come up with a different constant for each one of these experiments. If we were going to be doing more of an analysis of this, we might do that and take an average rate constant. We'll also see that there's other ways to figure out that rate constant. But just taking experiment number 1. So this is from experiment number 1. And we'll plug in the data. So we have a rate of 5.4 times 10 to the -7th meter or molarity per second of be careful of your units. And we're going to divide that by a concentration of the ammonium of 0.01 molar and a concentration of the nitrite of 0.20 molar. Which is going to give us a value for the rate constant of 2.7 times 10 to the -4th. And this is the one time we're going to want units for the rate constant, or for the constant. We need to come up with these. So if I kind of take a look up here at what I've got, obviously there's only seconds in that one place. So I know that seconds are going to be to the -1. It's going to be in the denominator. The molarity, I've got 1 molarity in the numerator that goes along with the rate, and I've got 2 molarities in the denominator. So we're going to end up with molarity to the -1 as well. So it would be the value of our rate constant there. Now if we look back at this data again, there's another way to come up with the rate law for the reaction. So let's go down here. Space, and what we're going to do is we know that the rate law has to be something of this form. Rate equals a constant, concentration of the ammonium ion raised to some power times the concentration of the nitrite ion raised to some power. Right. Now, if we're going to do the same thing, we're going to compare a couple of experiments. So we'll do experiment 1 and experiment 2. What we're going to do is divide one rate law, the rate law for the first experiment, by the rate law for the second experiment. Actually, we're going to flip that over, but we're going to find the ratio of the two to each other. Now, it's always easiest, or it's always going to work out better if you take the reaction that has the fastest rate and put that on top. So it would be experiment number 2. So if I take experiment number 2 and I put the rate for that one down, so I get 10.8 times 10 to the -7th, and that's going to be equal to the rate law constant. I'm going to put in the concentrations here, so 0.01 n raised to the n power and 0.200 raised to the m, and I made a mistake here. Let's fix that. All right, so there's the values filled in for experiment number 2. Now what I'm going to do is I'm going to divide that by experiment number 1. So I'm going to compare the rate. So this is the rate of experiment number 1, sorry, experiment number 2 compared to the rate of experiment number 1. So I've got 5.4 times 10 to the -7th. And I'm going to divide this side then also by those values. And this becomes particularly handy when the numbers get a little bit hard to deal with. Is that, what I'm doing here is I'm looking at it where I double the concentration of the ammonium ion, the rate double. But the numbers don't always work out quite that simply. So now as I do the math up here, obviously I end up with 2 over here on the left. And again, if we put the experiment with the larger rate on top, I'm going to end up with a whole number there, which will make things a little bit easier, is equal to the constants are going to cancel out. And notice that, again, I chose two experiments where I had the concentration of one of the reactants constant. So it doesn't matter what the value of m is, those are going to cancel out in both of those. So what I end up with then, if I do the division here, I get 0.01 I divide this, I get 2 raised to the n power. And so obviously for this statement to be true, n would have to be equal to 1. Now, if the numbers don't work out too nice for us, we end up having to use our logarithms. So to figure out the value of n, we would take the log of both sides, and we'll use log base 10. So if we take the log of 2, that's equal to log of 2 raised to the n power. And of course, from our pre-calculus, I would imagine, we know that the property of logs is that if we take the log of any number raised to the n power, we can put the log out in front. So we get n log of 2. And then it's a matter of plugging numbers into your calculator, or in this case, it's just a simple value of realizing that n is equal to 1. But again, that wouldn't necessarily be the case for all problems. Right, so this way is a little bit more involved than what we did the last way. But again, if the numbers get a little bit more complicated, or we're not sure how to explain, and that's particularly important here, that we have to be able to explain how we got those values for the exponents, for the n and the m. This is a very straightforward way to explain, all right, this is how I got the exponent on the ammonium ion to be 1. Now, what do these things mean? Well, either way that you get it, we end up with our rate law, which shows the relationship between the reaction rate and the concentration of the reactants. Again, when we get toward the end of this chapter, that's going to be very meaningful in us understanding what's going on in this reaction. The exponents tell the order of the reaction with respect to each reactant. In this reaction, they happen to be the same, but they don't always have to be the same. So in this one, it's first order in respect to the ammonium ion. So in other words, that first order is that value that we got up here, or that n equals 1. And first order with respect to the nitrite, again, that value that we got for m equals 1. The overall reaction order is then found by adding the exponents together. So overall, this would be a second order rate reaction. And again, we're going to use this information, this idea, later on in the chapter to try and understand a little bit better about what exactly is happening when these things react together.